For part 2, we'll be discussing listing and counting methods. For example 4, we're going to explore something called a tree diagram to list different possible outcomes. Suppose we roll a 4-sided die and toss a coin. What is the sample space? So unlike our prior examples, we actually have 2 parts to this experiment. Even though these could be done at the same time, we're going to view them as one happening before the other. So there's several ways to list every option. One of them is a tree diagram. So the idea is that we can either get a head or a tail when we toss the coin. If we get a head, we're going to have 4 options when we roll the die, 1, 2, 3, or 4. If we get a tail, again, same thing. We're going to have 4 options. So if we want to list our entire sample space, we can get a head and then a 1. Head and then 2, H3, H4, T1, T2, T3, T4. So that is our sample space. One thing to note here is that we had 2 options when we tossed the coin and 4 options when we rolled the die. So 2 times 4 gives you 8, so there's 8 possible outcomes. The question asked us to state our sample space, so we had to list all 8 options, but if I just wanted to know how many options there were, I could just multiply. Another way to list every option is by a table. The downside of using the table method, even though it is a little bit easier, is that it only works when you have experiments that have 2 parts or 2 steps to it. A tree diagram, however, could work for any number of steps. But doing this by a table, if we toss a coin, we have 2 options, heads or tails, and when we roll the 4-sided die, we have 4 options, 1, 2, 3, or 4. So that gives us H1, H2, H3, etc. Our same 8 options as before, but organized a little bit neater. So let's look at another example. Suppose a family has 3 children. What is the sample space for the option for the gender of each child, the youngest, the middle, and the oldest child? So again, we can have a boy or a girl for the first child. The middle child could either be a boy or a girl, and then the oldest child, the third child, or I should say the youngest child rather, can it be either boy or girl, boy or girl, boy or girl, boy or girl. So the sample space would be BBB, BBG, BGB, etc. Notice again that we had 2 options for the first child, 2 options for the second child, 2 options for the third child, so our sample space consists of 8 total options, 8 total possible outcomes. 2 times 2 times 2 is 8. This brings us to something called the fundamental counting principle. If we aren't interested in actually listing every possible outcome, but we're just interested in counting the number of possible outcomes, which is useful for probability, we can just multiply the number of possible outcomes for each part of the experiment. So let's apply it to a more common example. I'm sure you've been to stores where they say there are like 5,000 different flavor combinations, like maybe a sub shop or something like that. So let's explore an ice cream store. They have 3 different types of cones and 30 flavors of ice cream. So how many options are there when a customer orders a double scoop ice cream cone? So there's going to be 3 options. Well, we can just multiply. There's going to be 3 options for the number of cone types, 30 options for the bottom flavor, and 30 options for the top flavor. So it'd be 3 times 30 times 30, which gives you 2,700 wonderful flavor options. For example 7, suppose we have 5 people racing. How many different ways can they finish the race? So again, we can just multiply using the fundamental counting principle. There's, multiply the number of options for first, second, third, fourth, and fifth place. So if 5 people are racing, there's 5 different people that can place in first. However, once one of those people finish, there's only 4 options for second place. And again, once those first 2 people finish, there's only going to be 3 options left for third, etc. So it's just going to be 5 times 4 times 3 times 2 times 1. So 5 times 4 times 3 times 2 times 1 is 120. So there's 120 different ways in which 5 racers can finish a race. You might have seen this before in math classes, 5 factorial. This factorial symbol just means you're going to multiply down. So you're going to start off with whatever whole number you have. In this case, it was 5. And then you multiply by the next whole number down, which is 4, then 3, then 2, then 1. So 5 factorial will be 5 times 4 times 3 times 2 times 1. All right, so more generically, if we have n factorial, it has to be a whole number, but n factorial will just be n times n minus 1 times n minus 2, etc., 3 times 2 times 1. So, for example, 7 factorial will be 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5,040. N factorial is the number of ways in which we could rearrange those n objects. So 5 factorial is the number of ways in which we could rearrange 5 people. 7 factorial will be the number of ways in which we could rearrange 7 people. A few special cases to be aware of. 1 factorial is 1, which makes sense. If there's one person racing, there's one way in which he can finish. 0 factorial is a little bit more philosophical. I've seen a few interesting explanations of this. None of them are that great. But 0 factorial is also 1. And this is just something for you to know. Math breaks if this isn't true. So this is definitely true, but it's just one of those things that you just have to accept. For example 8, let's look at this example. So suppose again we have 5 people racing, but this time we don't really care about how everyone finishes. We just care about the top 3, how the top 3 place, who places in gold, silver, and bronze. So in this case, we're only going to have 3 things to multiply, 5 times 4 times 3, which is going to give us 60, first, second, and third. Notice, though, that this is just 5 factorial, but we dropped off the last 2, the 2 times 1. So another way to look at this is you could just do 5 factorial and divide it by 2 factorial. Obviously, that's a little bit more complicated, but that can be helpful when we have large numbers to work with. So this is going to give us a new formula. This new formula is called number of permutations. So number of permutations is when you have n objects, so like 5 people. We're selecting only r of them, so we only care about the top 3 finishers, for example. Each object can only be picked once, and the most important thing is that order matters. In other words, we care about coming in first versus coming in second versus coming in third. It's better to come in first. All right, so if you have all 4 of these things that we care about, we're interested in the number of permutations. We can use a symbol NPR, where N and R are just subscripts, to indicate the number of permutations. And to calculate it, if you were to do it by hand, you would use this formula. NPR is equal to just n factorial divided by n minus r factorial. And we're dividing by this n minus r factorial because we don't care about the last n minus r people. We only care about the first, the first few people. In our example where we had 5 racers and we picked 3 people, we only care about the first 3 people and we don't care about the last 2, 5 minus 3 being 2. I should note here that your textbook uses different symbols. They use capital N and lowercase n, where you're starting with n objects and you're picking lowercase n of them. This is a lot more consistent with just the basic vocabulary of statistics, where you have a population of capital N and a sample size of lowercase n. However, every kind of technology, any web applets that calculate NPR or any calculators that calculate it, use the symbols n and r instead of capital N and lowercase n. So I'm going to use this notation, but they're just letters. Use whichever letters you like. For number of combinations, so this is just a slightly change in how we're going to look at things. Basically, we're still dealing with number of permutations, but we don't care about the order. So that's going to give us a new term called combinations. So if we're interested in starting with 5 people and picking 3 of them, but we don't care about the order in which they finish, we're going to have to divide it by the number of ways we could rearrange 3 people, which is 3 factorial, or more generically, r factorial. So if we're interested in number of combinations, we're talking about we have n objects, we're selecting r of them. Again, each person can only be picked once, but this time order doesn't matter. We can use the symbol NCR to indicate the number of combinations, and that gives us this formula. So we see our permutations n factorial and divided by n minus r factorial, but we also have to divide it by r factorial to indicate that the order of those r people doesn't matter. Another common notation or common symbol to indicate number of combinations looks like this, n over r in a parenthesis. There's no division bar here. It's just n over r with parentheses. And again, that's just an alternative way of writing NCR. N over r is more common in more mathy-based classes, where NCR is more common in applied statistics type classes. So either way, they mean the same thing. The TI-84 calculator and TI-83 calculator uses the symbol NCR instead. Okay, so for example 9, suppose we have 4 faculty members that are randomly picked out of total 20 faculty members. And they're going to be picked to serve on a committee. So how many different committees are possible? Well, we're starting with n equaling 20. We're picking r equaling 4 of them. So we're interested, and again, order doesn't matter. Who cares, right? Who cares if you're picked first, second, third, or fourth to be on the committee? You just care that you're being picked to be on a committee. So it would be combinations. So it would be 20 over 4, or 20C4. If you were to do this by hand, it would be 20 factorial over 20 minus 4 factorial, 4 factorial. 20 minus 4 gives you 16. And then if we expand this out, I'd recommend stopping at 16 factorial on the top so the numbers don't get too large, because then you can cancel out those 16s, and then you have a more simple calculation to do. In fact, you can cancel everything out from the bottom if you like. But either way, you're going to get 4,845. An alternative way of doing this is just doing it on your calculator. So there are 4,845 possible committees when we're trying to select 4 faculty members out of 20 total faculty. Number of partitions. This is also called number of distinguishable permutations. So for example, how many different ways can we rearrange the letters of Mississippi? A little bit of a silly exercise, but how many ways can we do it? Well, there are, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 11 letters in Mississippi, so there should be 11 factorial different ways to rearrange the letters. But the problem is I can't tell the difference between some of them. There are 4 S's. I don't know which S is which. If I switched around these S's, it would look like the same word. So there's 4 factorial different ways to rearrange the S's. There's 4 factorial ways to rearrange the I's. There's 2 factorial ways of rearranging the P's. Summarize, right? We have 1 M, 4 I's, 4 S's, 2 P's. So we should take our 11 factorial and just divide it by the factorial of each of these, because that's the number of ways we can rearrange these letters, and we can't distinguish the difference between them. So it will be 11 factorial divided by 1 factorial, 4 factorial, 4 factorial, 2 factorial. Of course, you don't have to write the 1 factorial in here, but I like to do it because if you look, 1 plus 4 plus 4 plus 2 actually gives you 11. So it's a nice way to make sure you included every option. But anyway, that will give you 34,650 ways to rearrange the letters of Mississippi where you could actually distinguish them.